Now it's time to get into some of the chemistry based on a carbanion with two different moieties that engage in this. And we'll see that this chemistry ties in with multiple metabolic pathways. And so first let's look at thiamine pyrophosphate and this protonated Schiff base. So if we just take a quick look at this, what we see is resonance between the two. We see that here we've got a nitrogen with a positive charge, double bonded to a carbon, carbon single bonded to a carbonyl group. And that we have the same overall structure there. And so what we'll see is that they have similar chemistry and some differences, of course. So first of all, when we look at thiamine pyrophosphate, and this R group right there is the pyrophosphate, by the way. We'll see the whole structure in just a moment. But what we see is this resonance is important for both of these because of this carbanion. So we're going to go through 3 examples of TPP. We're going to look at commonalities to really hone in on understanding the chemistry and then being able to apply it even to a new situation. And then we'll look at differences based on the substrate and the product. This example over here, we will focus on transaldolase. Okay, so both of these combine again, right? That positively charged nitrogen, double bonded to a carbon, single bonded to a carbanion. And so that is this portion right here that is in equilibrium with this right here, resonance at least. Okay? And let's just get right to it. They're both going to attack a carbonyl group. Nothing new there, right? Nucleophilic attack to carbonyl groups is something that's tried and true. A lot of chemistry happens. So first of all, let's look at TPP. So there we go. So what we have is this R group over here, which is the pyrophosphate, and this aminopyrimidine ring. And so that's why we just look at R and R prime, because we don't need to worry about these. Those are our handles, right? They're important for the active sites, but they're not involved in the actual chemistry itself. And so this TPP is derived from vitamin B1. And so again, we've seen a number of times where these B vitamins, the reason we need them is they are essential cofactors for enzymes. And so when we look at this, what we see is that this is an acidic proton. And the reason this is an acidic proton, well, let's look down here. So this proton is removed, right? And we would, of course, always draw a base removing that. We wouldn't just say a proton leaves. So a base removes that, and then we have this carbanion. So what makes that stable, right? Why is this more acidic, right? So the reason this is more acidic, just look at the molecule and look at the structure, right? So when we look at this, what makes that negatively charged stable? And that's right, this positively charged nitrogen. So it's an electron sink. Not only that, right, and so we can understand that there is, the positive charge can stabilize a negative. But also this sulfur atom has some available d orbitals which can essentially accommodate some of the electron orbital clouds. It doesn't go fully into their sulfur, but there's room. So that sulfur is involved. So this is a thiazole ring. So when we look at that, we can go ahead and call that, right, thiazole ring. And of course, we would need something to get it to the negative charge. And so a Yllid molecule is a neutral molecule with one negatively charged atom, boom, attached to a positively charged heteroatom, and both of them have a full octet. So when you go ahead and count up the number of electrons, that's what you get. So let's start looking at some of these enzymes. But first, this pyruvate decarboxylase right here is involved in fermentation. So let's talk about the goal of fermentation first. Okay, so here we've got glucose to pyruvate glycolysis. That's all good. We know that pyruvate can then go through the citric acid cycle, and you generate lots of reducing equivalents in NADH, which then can travel to the electron transport chain, and that is used to generate ATP. Okay, so when we're looking at that perspective right there, that is when you need a lot of energy from ATP, and you have a lot of oxygen. It'll go that way. And we do that, yeasts do that, bacteria do that, right? Now let's look at something that we do, and that is we convert pyruvate to lactate. And we've looked at that before. Pyruvate to lactate, NADH. And so pyruvate, right, if we look at this NADH to NAD+, and we think of pyruvate, CH3, carbonyl group, and then a carboxylate group. Right? If you convert that carbonyl group to an alcohol, you get lactate. Okay, so that means that the carbonyl group was converted to an alcohol group. And that is no surprise because that is our first guess. Okay, so we do that lactic acid fermentation, homolactic fermentation, we do that. And then over here, what we yeast have these enzymes, and they convert through two steps, pyruvate to ethanol and carbon dioxide. So first of all, let's look at the fact that if we're going to go from pyruvate to ethanol and there's CO2, that means that we released, right, a carbon molecule. And so we have pyruvate, right, and we have ethanol, and we see that, yes, indeed, we lost the carboxylate through decarboxylation. So whether it is us doing homolactic fermentation or it is yeast undergoing two steps for ethanol fermentation, the purpose is to regenerate NAD+. So in times of low oxygen, whether it is our muscles, where we need energy fast, and we haven't started huffing and puffing and getting oxygen to our muscle tissues yet, right? In that intermediate, we start using energy really quick, then we run this right here. And by running this, the reason is that if we can't go here, how do we get our ATP? Well, instead, we run glycolysis over and over and over and over and over and over and over again, because we know that from glycolysis, for every round of glycolysis, we're getting ATP molecules out of it. And so we use that to drive our muscles. But to do so, we need NAD+. Right? So if we're running glycolysis and we're not running this, which regenerates NAD+, the citric acid cycle, how do we get our NAD+? We need NAD+ to run glycolysis. So what do? We convert pyruvate to lactate. That is from NADH to NAD+. That NAD+ is then available to keep running glucose. So when we look at the function, it is absolutely the regeneration of NAD+, because this can go back and support that reaction, can go back and support that reaction, just as this goes back and supports that reaction. Okay, so let's look at this step, which uses TPP. Right. Now, let's get our bearings here. We have thiamine pyrophosphate up here. We know this is the acidic proton due to the electron sink there and a little bit of electron density being able to go to the sulfur atom. We know that what's going to happen is we're going to decarboxylate pyruvate to acetaldehyde. So first step, deprotonation of TPP, carbanion attacks the carbonyl group, and this is the structure we have right there. So what we've done is we've created a carbon-carbon bond. Very common. When we have a carbanion, it can attack a carbonyl group to form a carbon-carbon bond. Then through electron rearrangement here, what we have is the release of electrons, right? So when we go here, these electrons are going down here to form a double bond, right? Which means that where did those electrons go? Over here. So we just broke that bond. That bond is now broken, which means carbon dioxide is released. We've got a double bond here, this shifts over there, and then we've got these resonance stabled molecule. So when you see this, we've got this lone pair, right, which can be donated here, which means that they've got too many electrons here, which go there, and then you've got a carbanion. So this right here is the resonance stabled carbanion, which in this case, it then attacks something, an acid, water, to pull that proton and protonates that carbanion. So at this next step, right? And what we're not showing is we're not showing the amino acids in the mechanism as part of the enzyme that's actually carrying this out. But we know that there would need to be some type of a base that pulls that off, right? And then releasing acetaldehyde. And that's how we get that. So let's look at it again. Okay, some things for you to fill in. Now what I've got here is we're looking at example 1, right, of TPP. We're going to go through several examples. So what I've got as a highlight for you is when you look at first, second, and third, that's the same set of steps for all of the mechanisms that use TPP that we're going to cover. And then down here, I've got it broken down to, for this particular enzyme, these are the next steps. So it's important for you to go through, fill this out, and really think through that. It might be useful for you to create your own chart of what is common and what is different. Deprotonation of the TPP forms the yllid. The strong nucleophilic carbanion attacks the carbonyl group, kicking those electrons to form that negatively charged oxygen, right? And really what happens is that gets protonated at the same time. So as far as I'm concerned, we can go ahead and have that arrow go like this. Pull off that proton, right, to form this hydroxyl group. And so that's what we have right here. So now what we have is, again, so what is driving this step? What is driving the step? Where are the electrons going? What is the more powerful thing? Where the electrons are being donated from, or what is attracting it? You need both, right? When we look at this, we've got our electron sink. Okay, so remember, carbon-carbon bonds are not real easy to break. But what we have here is, if you follow the flow of electrons, these electrons go here, which means that this is electron deficient. And so electrons go from here, and this is the carbon that is broken, the bond that is broken. All right, so there we go. We've broken that bond. And so when we look at this carbon-carbon breakage, right? So what's the leaving group here? What is the leaving group to get to from here to there? Right? The electron, the leaving group is whatever part the electrons go to. Right? So that would be carbon dioxide, leaving group. It leaves, right? Well, let's see. Electrons go there, okay? But then these electrons go here. Electrons go there. So the leaving group, what ends up with the electrons? The carbanion, right? So it's the TPP carbanion that is the leaving group. And we have carbon dioxide that is eliminated from the substrate. Now, this right here, common feature, right? Resonance stabilized carbanion, common feature of TPP containing enzymes. In this particular case, what do we need to do with what's on here? What does this need to become? This needs to become acetaldehyde, right? Well, we're not adding water to this, so the aldehyde needs to come from that hydroxyl group, which means that, right, we need to lose that proton, we need to form a double bond there, and we need to add a proton to where that carbanion is, right? CH3CH carbonyl group, acetaldehyde. So how we can do that? Well, we need to pull out the proton, and we need a proton there. We need to break that bond, and we need to form a carbonyl group. And so that's what we're seeing here up above. Right, in this base, right, if we want to talk about the enzyme regenerating, well, this base right there can now pull out that proton. Electrons kick down to form the carbonyl group. Breakage of the CC bond. Breakage of the CC bond. Let's always hone in on the pieces of the reaction that we need to follow along. We just broke that carbon-carbon bond. So what we did is, and then release acetaldehyde. And we have a stable yllid TPP. Now, when we look at what happens, we made a carbon-carbon bond, right? And then we broke a carbon-carbon bond. So we made it. Oh, excuse me, we broke a carbon-carbon bond here, right? So what we did is we made a carbon-carbon bond, we broke a carbon-carbon bond, we made a carbon-carbon bond, and we broke a carbon-carbon bond. Make it, break it, make it, break it, right? So the first carbon-carbon bond was between the carbon ion and the carbonyl group, right? Those carbons now have a carbon-carbon bond. Then we broke a carbon-carbon bond. That is the carbon dioxide being kicked off. We make another carbon-carbon bond. Where is it? So we make it, we break it. Ah, there it is. There's our carbon-carbon bond that we made. And then we need to go ahead and break a final carbon bond. Make it, break it, make it, break it. And so what do we have? We've got, right, we start out with a 3-carbon keto, alpha keto acid, right? Alpha keto acid, it's alpha to the keto. And it's converted to a 2-carbon aldehyde with the elimination of carbon dioxide.